Hey folks. Okay, what else can we figure out about stars from the HR diagram? Well, when you take a large sampling of stars, determine their luminosities, determine their temperatures, and plot them on an HR diagram, then you realize that stars tend to cluster up, right? Stars tend to fall into one of these four main classes, either the main sequence stars, the giants, the supergiants, or the white dwarfs. And 90% of the stars are main sequence stars. That's why it's called the main sequence, is because it's the main way that stars happen, right? And this spectral type, this letter here, is based on the color and the temperature, right? Where the O-type stars are the hottest, bluest ones, and then it goes down the alphabet O, B, A, F, G, K, M. I should say the alphabet of spectral types. So then the M types are the coolest and the reddest, right? So that one letter, that spectral type, in general, only tells you about temperature and color. Unless you're talking about main sequence stars, right? Because if you know you're dealing with a main sequence star, there we go, right? Then, because these main sequence stars cluster up along this tight little diagonal line, I mean, not a line, but, curve, then it turns out that there's a lot of stronger trends, right? That yes, the O-types are the hottest and the bluest, but also, if you're dealing with a main sequence star, then the O-types are also the brightest and highest luminosity. Why are they the highest luminosity and the hottest? Because they're the highest mass, right? Remember that, I said it before and I'll probably say it again, that the most important thing to know about a main sequence star is its mass, because the mass determines everything else. If a star is born with a high mass, then it's going to be up here on the main sequence, hot, blue, bright, and running out of fuel faster, right? Those high mass stars, in order to burn this brightly and this hotly, they have to run through their fuel in a short amount of time. And therefore they die faster, right? And then as you go down the main sequence, these stars are getting lower and lower mass, and because they are lower and lower mass, they are cooler, redder, and dimmer. But the upside of these stars being so cool and dim and red is that they don't have to burn their fuel very fast, and since they don't burn their fuel fast, they can live for a very long time until they finally run out of fuel. Okay. So if we know the luminosity and the temperature, what else can we figure out about these stars? Well, this is true for all stars, right? That all stars have a relationship between the radius, the luminosity, and the temperature like this, where if you know the luminosity and the temperature, you can calculate the radius of this star, and this equation is laid out in solar units. What do I mean by that? I mean, the luminosity is, you put the luminosity in solar luminosities, you put the temperature in Kelvin, and you get the radius of the star in solar radii. So in other words, how big is it compared to the sun? Right? This is true for all stars. If you know you're dealing with a main sequence star, then these two things are also true, right? The mass only determines, or I should say, the mass, you can determine the mass if you know the luminosity, right? The mass and the luminosity are related to each other like this, and a star with this mass must have this luminosity. So if you know the luminosity, and you know you're dealing with a main sequence star, I'll say main sequence only, right? Then you can figure out how much mass that star must have. And then once you know the mass of the star, then you can plug it into here and determine how long that star will live from birth to death. How long will it take to run out of hydrogen fuel? And that'll determine how long that star lives on the main sequence. Okay, well, let's get some practice here. Okay, so a star with... Here, we can make some room here. All right. So, a star with 0.167 solar luminosities. So, this is what... Now, this is kind of weird, right? Because stars have such very different luminosities, right? From the very dim ones up here to the very bright ones up here. The range of numbers gets huge. And therefore, in order to take this giant span of numbers and squish it down onto a reasonably sized chart, you scale this logarithmically, right? Where it goes up powers of 10. Or down powers of 10, I suppose, in this case. So, this is 1. What is 10 to the negative 2? 10 to the negative 2 is 0.01. 10 to the negative 4 is 0.0001. So then a star with a luminosity of 0.1 will be right about here. Right? In between 1 and 0.01. So let's say that star, that first star here, has a luminosity of about there, and a temperature of 4,480 Kelvin, which puts it at, so let's see, if this is 2,000 and this is 4,000 and this is 6,000, then 5,000 will be about there, which means almost 4,500 will be about there. So we'll say, okay, that star has this luminosity and this temperature. Okay, so that star is right about there. What kind of star is that? That's a main sequence star. Okay, so that's a main sequence star. What is its spectral class if it's main sequence? That sure looks like a K-type star. Right, because its temperature's right there in the K-type range. All right, what about a star with a luminosity of 500 solar luminosities? Well, 10 to the second, right? 10 to the second is 100. 10 to the fourth is 10,000. So then 1,000 must be right about there. There's 1,000. In which case 500 is going to be right about, well, you might think it's in the middle, right? Between 100 and 1,000, 500 will be right about there. And actually, if we're being really careful, it's a little higher than halfway up. So let's say that's about 500. 500, let's call it 510. But a temperature of 3,500, which, okay, that's probably 3,000. So that's going to be 3,500. So a temperature of, where am I going here? Temperature like this, and a luminosity like that. Going pretty carefully. Okay, so that star is right about there. Which, what kind of star is that? That's a red giant. Right, that's on the red giant branch right there. What spectral class is it if it's a main sequence? Well, it's not a main sequence, so don't need to worry. All right. So 18 solar luminosities, 8,800 Kelvin. Well, let's see. If this is 1, I sort of doodle here initially. I'm going to do a little better. So 10, if this is 1 and that's 100, then 10 is about there. And if this is if this is 10,000 Kelvin and that's 8,000 Kelvin, then 9,000 Kelvin will be right about there. And so we'll say, okay, this star is about 10 solar luminosities and about 9,000 Kelvin, which says, okay, if that's there, and that's there, so that's right about there, which is, I think when I did this the first time, it was a little bit off over here, but, second time's a charm. Oh, well, okay, didn't draw that quite straight, did I? Still, that's on the edge of the main sequence. So still close to the main sequence, but like getting close to the edge. But yeah, still a main sequence star. What's the spectral class? Well, that's pretty much smack dab in the F-type range. Okay. All right. Now let's do some calculations here. All right. We're given the spectral type, BGM type. We figured out the luminosity. We figured out the temperature. What is the radius, the mass, and the lifetime? And we're told they're all main sequence stars. All right, so we know they're main sequence stars, which means we can figure out the radius, the mass, and the main sequence lifetime. Let me pull up my spreadsheet here. Okay. Well, let's see. Like I laid out before, I'm going to take my... How should we do this? I think since we're putting our inputs in the left column and our outputs in the right column, right? The things that we're entering and the things that we're calculating. Let's do it like this. We will put the luminosity and the temperature here. And the luminosity needs to be in solar luminosities, and the temperature needs to be in Kelvin. And using that, we'll calculate the radius, the mass, and lifetime. Okay. So for our first, since I got the equations, since I pulled up the equations here again, let's put the formula in first here, even though it's not going to give us a good answer. You know what? I'll put in some dummy numbers here for the moment. All right, let's see, the sun, right? If it's a 1 solar luminosity star, right, that's the sun. What's the surface temperature of the sun? 5,800 Kelvin. So I'm just going to put in some numbers there. That way it's got some numbers to do the math with. All right. What's the radius? Well, the radius equals, I'll open parenthesis, the luminosity, right? Grab the luminosity, raise it to the 0.5 power. All right, that's my numerator. And then I'm going to divide by, open parenthesis in the denominator, the temperature divided by 5,800 Kelvin, and then raise that to the second power. Okay, so I've got luminosity to the 1/2 on top, temperature over 5,800 squared on the bottom. I'm dividing them. Okay, so there we go. If we have a star that is the same luminosity as the sun and the same temperature of the sun, what's the radius? Well, remember this formula gives us the radius in solar radii. So it turns out that star, if it's just as bright and just as hot as the sun, then it shouldn't be no surprise. That star is the same size as the sun. It's the same radius as the sun. 1 solar luminosity. All right. The mass equals the luminosity raised to the power of 1 over 3.5. Careful here, right? Careful. Like we've seen before, the spreadsheet knows the order of operations. So if this is what I put, it would take the luminosity, raise it to the first power, and then divide that by 3.5, which is not what we want, right? We want the formula to take the luminosity and raise the luminosity to the power of 1 over 3.5. So we got to put these parentheses here to make sure that it raises the luminosity to the right exponent. All right. And this is what, right? This equation gives us the mass in solar masses. So again, why does this main sequence star have the same luminosity as the sun and the same size as the sun? Because it's the same mass as the sun. Right? And then the lifetime. What's the lifetime of a main sequence star? Well, it equals 1 times 10 to the 10th power, right? 1e10, 1 times 10 to the 10th power, times the mass, raised to the negative 2.5 power. Right? So there we go. Ooh, yeah, well, stars live a long time. That's going to be a lot of zeros, and I don't want that. I want that in scientific notation. So what do? Right click, go to Format Cells, give me that as in scientific notation. Okay, so that star is going to live. I mean, we've already seen this is a star like the sun, same mass as the sun, so it's going to live the same lifetime as the sun, 1 times 10 to the 10 years. All right. Now we can make short work of these questions here. Make some more room on the screen. You know what? I'll put this up here. Put that down there. Okay. We're good to go. All right. So this B-type star has a luminosity of 3,160 solar luminosities and a temperature of 18,600 Kelvin. That's a hot star. Why is this star so hot and so bright? Well, because it's 5.5 times the size of the sun. So 5.47. Why is it so big and so hot and so bright? Well, because it's a lot more massive than the sun is. It's 10 times the mass of the sun. But if that star is so massive, it's going to burn through that fuel faster. How long is that star going to live? It's only going to live... You could put 3.16 times 10 to the 7 years, but what does that mean? What is 10 to the 7? 10 to the 7 is 10 million years. So that means that star is going to live 31.6 million years. But of course, you wouldn't write down 31.6 million years. You would write down 3.16 times 10 to the 7 years because scientific notation makes life easier. All right. How about this G-type star? Well, we already kind of figured out the answers, didn't we? Well, it's a star that's the same luminosity as the sun. It's the same temperature as the sun. What could the properties of that star be? Well, of course it's going to be the same radius, the same mass, and the same lifetime as the sun, because the sun is a G-type main sequence star. So same. Okay, what about this cooler star? What about this M-type star? 0.015 solar luminosities at a temperature of 3,150 Kelvin. So this is what? This is a pretty small star, right? 0.42 times the radius of the sun. Only 0.3 solar masses. And it's going to live 2.01 times 10 to the 11 years. Let's look at these numbers here for a second, right? This B-type star, it's hotter, it's brighter than the sun. Why is this? Remember, if you know that you're dealing with a main sequence star, you know pretty much everything about it, right? Why is this star so bright and so hot? Because it's high mass, right? And if it's higher mass, it's also going to be larger. But the downside of having a high mass star is it's only going to live for 30 million years. Right? What about this M-type star? This M-type star, it's dim, it's cool, it's red. Why is it so dim and so cool? Because it's lower mass. And if it's lower mass, it's also going to be smaller. But the upside of having a low mass is that this star is going to live for 2 times 10 to the 11 years, right? What is that? 200 billion years, right? Our sun is going to live for 10 billion years. This star is so dim and it's burning that fuel so slowly, it's going to live for 200 billion years, which is objectively a long time. All right. So let's look at the rest of these questions here. All right. So between the O-type stars and the M-type stars, which one's hottest? The O-types are hottest. Which ones are smallest? Now remember, if we're dealing with main sequence stars, right, the temperature tells you pretty much everything, right? If you're dealing with main sequence stars, then the hot ones are also the big ones. So, just like the numbers we saw here, the M-types must be the smallest. Which ones have the lowest mass? The M-types. Which ones are blue? Oh. Which ones are brightest? Which ones are brightest? The hot ones are. Which one have the longest lifetimes, though? The low mass, the cool, the red ones. There we go. I realize now it doesn't explicitly say that that these are main sequence. So no. If the M-type and the O-type stars are both main sequence stars, right? Because remember, the spectral type, O or M, only tells you temperature and color, but if you know you're dealing with main sequence, then you can figure out all these other things too. All right. So like I say, if you know you're dealing with a main sequence star, life is easy because you know everything. Why? Why do you know everything? Because all of these properties, the temperature, the size, the color, the luminosity, the lifetime, they're all controlled by the mass of the star. If you know the mass of the star, you know everything. So, this is why main sequence stars are so easy to study. Right? Once you get into the other spectral class, or the other stellar types, right? Once you get into the red giants, the supergiants, the white dwarfs, then things get a little more complicated and a little more interesting. But if you know you're dealing with main sequence, you got all the answers, if you know the mass. All right. So, hopefully that's making some sense. Post your questions to the discussion board if you've got them. And hopefully that's making sense. Keep going. Keep moving. Have a good one, everybody.